and woman to be holding hands, but decided it might make the Earthlings look like a single creature with two heads. We began as wanderers, and we are wanderers still. We have lingered long enough on the shores of the cosmic ocean. We are ready at last to set sail for the stars. Carl Sagan. The Arecibo Message. While the search continued for beacons set up by intelligent beings and likely star systems, Drake and Sagan decided to send planet Earth's own "We Are Here" signal. The 3-minute burst of 1,000 kilowatts radio waves was designed to cross distances separating stars. Beamed out from the Arecibo radio dish in Puerto Rico in November 1974, the interstellar message was aimed at the globular cluster M13, a group of about 300,000 stars 25,000 light-years from Earth. Instead of pictograms, the Arecibo message took the form of densely packed mathematical code, consisting of 1,679 binary digits. The digital message contained the numbers 1 to 10 and information about the identity of the sender, details about DNA, the overall shape and dimensions of a human, and the position of planet Earth. One of the hopes that accompanied the robotic explorers, as they were dispatched across the solar system from the 1960s onward, was that they might uncover some indication of extraterrestrial life within the solar system itself, even if it were only single-celled organisms. The spacecraft that touched down on planets, such as NASA's Viking landers on Mars, carried experiments to test for signs of life. To date, no indication of life, either past or present, has been found, although some unexplored corners of the solar system remain candidates for life, such as the deep oceans thought to lie beneath the frozen surface of Jupiter's moon Europa. The Arecibo message was broadcast into space a single time in 1974. Coded in binary, its message is arranged in 73 rows of 23 columns. Continued silence. No reply has ever been received to any of the 10 interstellar radio messages sent since 1962, and no communication has been detected. However, there have been false alarms. The most famous of these came in 1977, when an inexplicably powerful blast of radio signals was recorded coming from the direction of the Chi Sagittarii star system by Jerry Emin at Ohio State University. He circled the signals on the readout and wrote "wow" next to them. The "wow" signal was never found again, however, and recent research suggests that it may have come from a hydrogen cloud surrounding a comet. Given the vast distances between stars, it is still early days, however. The Arecibo message will not reach its target stars for another 25,000 years. Neither the Pioneer plaques nor the gold-plated discs carried by Voyagers 1 and 2, the Voyager Golden Record, are headed toward any particular star system. Unless they are intercepted, they are destined to wander the Milky Way eternally. Sagan, for his part, believed that to find life or to fail was a win-win scenario. Either result would show something important about the nature of the universe. Carl Sagan stands next to a model of the Viking 1 lander. The lander sent back signals from the surface of Mars from 1976 to 1982. Its instruments found no sign of life. SETI in the modern age. NASA struggled to maintain its SETI funding, and today SETI is privately funded. Since the 1980s, the mantle has been taken up by the SETI Institute, based in Mountain View, California. UCal, Berkeley, through its SETI at Home initiative, harnesses a network of volunteer computers to trawl Arecibo observatory data for patterns that might indicate an unnatural radio source. Meanwhile, in 2016, China announced the completion of the largest ever radio telescope, the 500-meter aperture spherical telescope. Among other things, FAST will search for extraterrestrial communications. It will eventually be made available to researchers from around the world. In recent years, the focus of SETI has moved away from merely listening for messages. Efforts have been directed toward picking up biochemical signs of life or indications of advanced technology. Alien life should leave its signature in evolved planetary atmospheres, volatile molecules, or complex organic chemicals that could only be created by life processes. Highly technological societies may have learned how to harvest the energy of their star. A Dyson sphere megastructure completely or partially surrounding a star to capture its energy would affect the star's observed output. It may also be possible to observe signs of asteroid mining or directly detect extraterrestrial spacecraft. The SETI Institute's Allen Telescope Array in California is used daily to search for possible alien communications, as well as for radio astronomy. A cautious approach. In 2015, the Breakthrough Initiatives program was launched with the backing of Russian billionaire Yuri Milner. In addition to a $1 million prize pool for SETI research and a plan to send a fleet of spacecraft to a nearby star, an open competition was announced to design a digital message to be sent to an extraterrestrial civilization. The Breakthrough Message Project aims to accurately and artistically represent humanity and Earth, but pledges not to transmit any message until the risks and reward of contacting advanced civilizations have been debated. Voyager 1 sent back this image of Earth from beyond the orbit of Pluto. The pale blue dot appears in a band of scattered sunlight. Looking at ourselves. In 1990, Carl Sagan persuaded Voyager 1's controllers to swivel its camera back toward Earth. From 4 billion miles away, the craft captured the pale blue dot image. Sagan wrote, "Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam." Sagan stressed the importance of looking at ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for the moment the Earth is where we make our stand. SETI represents a series of questions whose answering would tell us about Earth's place in the universe, whether the Copernican principle is correct, and if so, where else life has evolved. The answers could eventually provide humans with a way to transcend their origins and become a galactic species. We are almost certainly not the first intelligent species to undertake the search. Their perseverance will be our greatest asset in our beginning listening phase. Project Cyclops Report, NASA. Carl Sagan. Carl Sagan is one of the most widely known 20th-century scientists. His deep, honeyed tones are the instantly recognizable voice of the documentary series Cosmos. Sagan was raised in a working-class Jewish area of New York and as a boy was an avid reader of science fiction. A talented pupil, he went to the University of Chicago in 1951 on a full scholarship. Sagan received his Ph.D. in 1960, showing that the high surface temperatures of Venus are due to a runaway greenhouse effect. Sagan conducted pioneering research in planetary science and exobiology, which many in mainstream astronomy viewed with suspicion. In 1985, he wrote the sci-fi book Contact, which was later turned into a movie. With his visionary, positive, and humanist outlook, the Cornell University professor inspired a new generation of astronomers. Key works: 1966 Intelligent Life in the Universe. 1983 Cosmos. See also, Radio Telescopes, The Space Race Exploring the Solar System, Exoplanets. Shklovsky-Carter Tartar. In Context. Key astronomers Anthony Hewish, Jocelyn Bell Burnell. Before 1932 English physicist James Chadwick discovers the neutron. 1934 Walter Baade and Fritz Zwicky proposed that stars that explode as supernovae leave behind collapsed remnants made of closely packed neutrons, which they named neutron stars. After 1974 American astrophysicists Joseph Taylor and Russell Hulse discover two neutron stars, one of them a pulsar, orbiting each other. 1982 American astrophysicist Donald Backer and colleagues discover the first millisecond pulsar, which spins 642 times per second. In the late 1950s, astronomers across the world started to find mysterious, compact sources of radio signals in the sky without any corresponding visible objects. Eventually a source of these radio waves was identified, a faint point of light, which became known as a quasar. In 1963, Dutch astronomer Martin Schmidt discovered a quasar that was hugely distant. The fact that it was so easily detected meant it must be pouring out energy. Searching for quasars. By the mid-1960s, many radio astronomers were searching for new quasars. One such figure was Anthony Hewish, part of a radio astronomy research group at Cambridge University. Hewish had been working on a new technique in radio astronomy based on a phenomenon called interplanetary scintillation, which is a twinkling, or fluctuation, in the intensity of radio emissions from compact radio sources. The twinkling of sources of visible light, such as stars, is caused by disturbances in Earth's atmosphere that the light has to pass through. The twinkling of radio sources, however, is caused by streams of charged particles emanating from the sun. As radio waves pass through this solar wind, they are diffracted, meaning that the waves spread out, making the radio source appear to twinkle. Hewish hoped that IPS could be used to find quasars. Radio waves coming from a compact source, such as a quasar, twinkle more than radiation from a less compact source, such as a galaxy, and so quasars should twinkle more than other radio sources. Hewish and his team built a large radio telescope designed specifically to detect IPS. It covered an area of nearly 4.5 acres, took 2 years to construct, and required more than 120 miles of cable to carry all the signals. Members of the Cambridge Radio Astronomy Group built the new telescope themselves. Among them was a Ph.D. student named Jocelyn Bell. When the telescope started operating in July 1967, Bell was made responsible for operating it and analyzing the data, under the supervision of Hewish. Part of her job was to monitor output data from the telescope, made by pen recorders on chart recorder printouts. Examining about 100 feet of chart paper every day, Bell quickly learned to recognize scintillating sources. Little Green Man 1. About 2 months into the project, Bell noticed an unusual pattern of signals, which she described as scruff. It looked far too regular and had too high a frequency to be coming from a quasar. Checking back through her records, she found it had appeared in the data before and always came from the same patch of sky. Intrigued, Bell started making more regular chart recordings of the same area of sky. At the end of November 1967, she found the signal again. It was a series of pulses, equally spaced and always 1.33 seconds apart. Bell showed the signal, dubbed Little Green Man 1, to Hewish. His initial reaction was that a pulse occurring every 1.33 seconds was far too fast for something as large as a star, and the signal must be due to human activity. Together, Bell and Hewish ruled out various human-related sources, including radar reflected from the moon, Earth-based radio transmissions, and artificial satellites in peculiar orbits. A second telescope was also found to pick up the pulses, which proved that they could not be due to an equipment fault, and calculations showed that they were coming from well outside the solar system. Hewish had to revise his opinion that the signals had a human origin. The possibility that they were being sent by extraterrestrials could not be ruled out. The team measured the duration of each pulse and found it was only 16 milliseconds. This short duration suggested that the source could be no larger than a small planet. But a planet, or an alien civilization living on a planet, was unlikely, since the signal would show slight changes in frequency, called Doppler shifts, as a planet orbited its star. This image of a pulsar in the Crab Nebula, a well-known supernova remnant, was taken in space by the Chandra X-ray Observatory. The white dot at the center is the neutron star. Publishing dilemma. Hewish, Bell, and their colleagues were unsure how to publish their findings. While it seemed unlikely that the signals were being sent by an alien civilization, no one had any other explanation. Bell returned to her chart analysis, and soon found another scruff in a different part of the sky. She discovered it was due to another pulsating signal, this time slightly faster, with pulses every 1.2 seconds. Now she was reassured that the pulses must have some natural explanation. Two sets of aliens in different places would surely not be sending signals to Earth at the same time and at nearly the same frequency. By January 1968, Hewish and Bell had found 4 pulsing sources in total, which they decided to call pulsars. They wrote a paper describing the first source, suggesting that it might be due to pulsed emissions from a theoretical type of superdense collapsed star called a neutron star. Objects of this type had been predicted as long ago as 1934, but up to that time had never been detected. My eureka moment was in the dead of night, the early hours of the morning. But when the result poured out of the charts, you realize instantly how significant this is. What it is you've really landed on, and it's great. Jocelyn Bell Burnell. Explaining the pulses. 3 months later, Thomas Gold, an Austrian-American astronomer at Cornell University in the US, published a fuller explanation for the pulsed signals. He agreed that each set of radio signals was coming from a neutron star, but proposed that the star was rapidly spinning. A star like this would not need to be emitting pulsed radiation to account for the pattern of signals observed. Instead, it could be emitting a steady radio signal in a beam that it swept around in circles, just like a beam of light from a lighthouse. When the pulsar's beam was pointing at Earth, a signal would be detected, which would show up as the sort of short pulse that Bell had noticed on printouts. When the beam had passed by Earth, the signal would stop until the beam came around again. Challenged about the pulsation rates, which implied extremely rapid spinning, Gold explained that neutron stars could be expected to behave in this way because of the way in which they form, from the collapse of stellar cores in supernova explosions. A pulsar is a spinning neutron star with an intensely strong magnetic field. It emits beams of radiation from its north and south poles. Confirming the hypothesis. Initially, Gold's explanations were not well received by the astronomy community. However, they became widely accepted after the discovery of a pulsar in the Crab Nebula, a well-known supernova remnant. Over subsequent years, many more pulsars were found. They are now known to be rapidly rotating neutron stars with intense electromagnetic fields, which emit beams of electromagnetic radiation from their north and south poles. These beams are often, but not always, radio waves and sometimes other forms of radiation, including in some cases visible light. One reason for the excitement regarding the discovery of pulsars was that it increased the likelihood that another theoretical phenomenon, black holes, might also be detected and proven. Like neutron stars, black holes are objects that could result from the gravitational collapse of a stellar core following a supernova explosion. In 1974, Hewish and Martin Ryle shared a Nobel Prize, Ryle for his observations and inventions, and Hewish for his decisive role in the discovery of pulsars. However, Jocelyn Bell Burnell was told that she would not share the award with them because she had still been a student at the time of her work. She graciously accepted that decision. A spinning neutron star that is emitting radiation beams can be detected as a pulsar on Earth if, as it spins, one or possibly both of its radiation beams recurrently point in Earth's direction as they are swept around through space. The pulsar will then be detected as a very regular series of signal blips. Jocelyn Bell Burnell. Jocelyn Bell was born in 1943 in Belfast, Northern Ireland. After earning a physics degree from Glasgow University in 1965, she moved to Cambridge University, where she studied for a Ph.D. there. She joined the team that built a radio telescope to detect quasars. In 1968, Bell became a research fellow at the University of Southampton and changed her last name to Bell Burnell when she married. She has held astronomy and physics-related positions in London, Edinburgh, and at the Open University, where, from 1991 to 2001, she was professor of physics. From 2008 to 2010, she was president of the Institute of Physics. Bell Burnell has received numerous awards for her professional contributions, including the Herschel Medal of the Royal Astronomical Society in 1989. In 2016, she was visiting professor of astrophysics at Oxford University. Key work: 1968 observation of a rapidly pulsating radio source. See also, radio astronomy, supernovae, quasars and black holes, discovering black holes. Ryle. In context. Key astronomer: Beatrice Tinsley. Before 1926, Edwin Hubble produces a classification for galaxies based on their shapes. Early 1960s, American Alan Sandage proposes that disk galaxies form through the collapse of large gas clouds. He estimates distances to remote galaxies based on the idea that the brightest galaxies have similar luminosity. After 1977, Canadian Brent Tully and American Richard Fisher find a link between the luminosity and rotation of spiral galaxies. This is useful in estimating distances to spiral galaxies. 1979 Vera Rubin uncovers a discrepancy between actual and predicted rotational velocities in spiral galaxies, giving evidence of unseen dark matter in such galaxies. Until a young New Zealand astronomer named Beatrice Tinsley published a highly original thesis in 1966, the methods used by cosmologists to calculate the distances to remote galaxies had been flawed. Accurate data for these distances was important because it would help to answer some of cosmology's most fundamental questions, namely the average density of the universe, its age, and its rate of expansion. One method used in the 1960s was based on the idea that galaxies of the same type should all have roughly the same intrinsic brightness. On this basis, it was thought that distances to faraway galaxies should be obtainable simply by measuring their light output and comparing it to those of nearby galaxies of the same type whose distance was known. Tinsley's argument. Tinsley challenged this approach, saying it was crude and unreliable. In calculating galaxy distances, she argued, more consideration had to be given to the fact that galaxies evolve over time. The light from remote galaxies can take millions or billions of years to reach Earth, where the galaxies are seen as they were in the distant past. The farther away they are, the earlier they appear in their stage of evolution. In other words, a distant galaxy that appears elliptical may be quite unlike a closer, known elliptical galaxy. In calculating distances to remote galaxies, she argued, corrections needed to be applied, based on the factors that change as galaxies evolve, specifically the abundance of different chemical elements and the rate of star birth. Tinsley outlined ways in which galaxies evolve in terms of their brightness, shape, and color. The stars and the non-stellar material in galaxies change over long periods. For example, some stars eventually turn into giant stars and get brighter as they age, star formation rates change as gas and dust are used up, and the interstellar medium is enriched with elements heavier than helium and hydrogen as old stars die. Galaxy models. Tinsley's thesis was described as extraordinary and profound by her peers at the University of Texas. For the rest of her short career, she continued studying the ways in which different populations of stars age and affect the observable qualities of galaxies. From this, she developed models of the ways in which galaxies evolve, which combined an understanding of stellar evolution with knowledge of the motions of stars and nuclear physics. Today, these models form the basis for studies of galactic evolution. They also provide information about what protogalaxies might look like. Tinsley's work also contributed to research on whether the universe is open or closed. One of the most insightful theoreticians in astronomy over the past century, Tinsley has been described as opening doors to the future study of the evolutions of stars, galaxies, and even the universe itself. This artwork depicts the night sky from a hypothetical planet within the Milky Way, when the galaxy was just 3 billion years old. The sky is ablaze with the hydrogen clouds of new star birth. Beatrice Tinsley. Beatrice Hill was born in Chester, UK, in 1941, and moved with her family to New Zealand when she was 4 years old. In 1961, she received a degree in physics from Canterbury University, and in the same year married classmate Brian Tinsley. In 1963, they moved to Dallas, Texas, where her husband had been offered a university job. Beatrice wasn't allowed to work at the same university, so she took a teaching job at the University of Texas at Austin. In 1966, she completed her Ph.D. with a thesis on the evolution of galaxies. Tinsley soon became an influential figure in the field of cosmology. In 1974, she took a position as assistant professor at Yale University, becoming the university's first female professor of astronomy in 1978. She died of cancer in 1981, at just 40. Mount Tinsley in New Zealand is named in her honor. Key work. 1966 Evolution of Galaxies and its Significance for Cosmology. See also, Measuring the Universe, the Birth of the Universe Beyond the Milky Way. Nuclei and Radiation, the Primeval Atom, Dark Matter. In context. Key organization: NASA, Apollo. Before 1957, the Soviet Union surprises the US by launching the first satellite, Sputnik 1. 1961 cosmonaut Yuri Gagarin is the first person to travel into space and to orbit Earth. After 1975, the first joint US-USSR space project officially marks the end of the space race. 1994, 1998 US and Russian space agencies share skills and expertise during the Shuttle-Mir program. 2008 Indian lunar mission Chandrayaan-1 finds evidence of widespread water ice on the Moon's surface. 2015 Chinese rover YouTube discovers distinct layers of rock, including a new type of basalt, on the Moon. In the early 1960s, the US lagged behind the Soviet Union in the space race. The Soviets had launched the first satellite in 1957, and on April 16, 1961, Yuri Gagarin became the first human in space. In response, in 1961 US President John F. Kennedy publicly committed to landing a man on the Moon before the end of the decade. The project was carefully chosen. Landing on the Moon was so far beyond the capabilities of either protagonist that the Soviets' early lead might not seem so significant. Despite the reservations of many at the time regarding a moon landing's scientific value, especially given the dangers and technical complexities involved, human spaceflight was now the focus of the US space program. NASA managers felt that with enough funding they could put a man on the Moon by 1967. NASA Administrator James H. Webb suggested another 2 years be added as a contingency. In those 6 years from 1961 to 1967, NASA tripled its workforce, even though most of the planning, designing, and building of the hardware was undertaken by private industry, research institutes, and universities. NASA claimed that only the construction of the Panama Canal and the Manhattan Project to develop the nuclear bomb rivaled the effort and expense of the Apollo program. I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the Moon and returning him safely to the Earth. John F. Kennedy. Project Mercury astronaut John Glenn enters the Friendship 7 on February 20, 1962. His mission, lasting just under 5 hours, was the US's first manned orbital spaceflight. Which way to the Moon? At the time of Kennedy's historic announcement, the US boasted a grand total of 15 minutes of human spaceflight. To move from here to a moon landing, many technological hurdles needed to be overcome. One of the first was the method of getting to the Moon. 3 options, known as mission architectures, were on the table. The direct ascent profile, or all the way, required an enormous multistage rocket with enough fuel on board to transport the crew back to Earth. This was initially the favored approach. However, it was also the most expensive, and doubts were raised over the feasibility of building such a monster rocket before the 1969 deadline. In the Earth orbit rendezvous profile, a moonbound rocket ship would be assembled in space and dock with modules that had already been placed in orbit. Lifting things into space is the most energy-consuming part of any off-Earth mission, but multiple rocket launches would sidestep the need for a single spaceship. This was the safest option. But it would be slow. The real weight savings came with the lunar orbit rendezvous profile. Here, a smaller rocket would put a 3-part spaceship on course to the Moon. At the Moon, a command module would remain in orbit with the fuel for the journey home, while a lightweight 2-stage lunar lander would be sent to the surface. This quick and comparatively cheap option carried with it the very real risk of leaving a crew stranded in space should anything go wrong. After much debate and lobbying, influential figures, such as Wernher von Braun, director of NASA's Marshall Space Flight Center, threw their backing behind LOR, and in 1962, LOR was chosen. This was the first of many leaps of faith for Apollo. Technological hurdles. On February 20, 1962, John Glenn became the first American to orbit Earth, looping 3 times around the planet in Friendship 7, as part of the US's first spaceflight program, Project Mercury, which ran from 1958 to 1963. 3 more successful Mercury flights followed, but there was a big difference between operations in low Earth orbit and landing on the Moon. An entire new fleet of launch vehicles was required. Unlike Mercury spacecraft, which carried a single astronaut, Apollo missions would need a crew of 3. In addition, a more reliable power source was needed and much more experience in space. The world's first fuel cells were built to provide the power. Project Gemini, NASA's second human spaceflight program, provided the skills, with endurance spaceflights, orbital maneuvers, and spacewalks. Scientists also needed to know more about the moon's surface. A deep layer of dust could swallow up a spacecraft and prevent it from leaving, clog up the thrusters, or cause the electronics to malfunction. Unmanned fact-finding missions were mounted in parallel with Apollo, but the first wave of robotic explorers dispatched to the moon was an unmitigated failure. 6 Ranger landers failed on launch, missed the moon, or crashed on impact, causing the program to be nicknamed Shoot and Hope. Luckily, the final 3 Rangers were more successful. Between 1966 and 1967, 5 lunar orbiter satellites were placed in orbit around the moon. They mapped 99% of the surface and helped to identify potential Apollo landing sites. NASA's 7 Surveyor spacecraft also demonstrated the feasibility of a soft landing on the lunar soil. The Saturn V rocket was developed for the Apollo program. Many private corporations were involved in its production, including Boeing, Chrysler, Lockheed, and Douglas. Gene Kranz. A gamble and a disaster. At 363 feet, Saturn V, the heavy-lift booster that carried the Apollo astronauts out of Earth's atmosphere, is still the tallest, heaviest, and most powerful rocket ever built. Man rating, the rocket proved particularly troublesome. The mammoth engines generated vibrations that threatened to break the rocket apart. Knowing that the project was behind schedule, NASA's associate administrator for manned spaceflight, George Mueller, pioneered a daring, all-up testing regime. Rather than the cautious stage-by-stage approach favored by von Braun, Mueller had the entire Apollo, Saturn systems tested together. While striving for perfection, the NASA engineers developed a new engineering concept, that of redundancy. Key or critical components were duplicated in order to increase overall reliability. The Mercury and Gemini projects had taught engineers to expect unforeseen risks. A fully assembled Apollo vehicle had 5.6 million parts, and 1.5 million systems, subsystems, and assemblies. Even with 99.9% reliability, the engineers could anticipate 5,600 defects. Nevertheless, over its 17 unmanned and 15 manned flights, the Saturn boosters had shown 100% reliability. With 2 partially successful test flights under its belt, Mueller declared that the next launch would carry astronauts. Until 1967, progress had been smooth, despite the breakneck pace. Then disaster struck. An electrical short circuit during a launch rehearsal started a fire that incinerated the Apollo 1 crew inside the command module. The toxic smoke and intensity of the fire in a pressurized, pure oxygen atmosphere killed Virgil, Gus Grissom, Ed White, and Roger Chaffee in less than 5 minutes. In the wake of this tragedy, the next 5 Apollo missions were unmanned tests. Modifications were made, resulting in a safer spacecraft with a new gas-operated hatch, a 60-40 oxygen-nitrogen mix in the cockpit, and fireproof wiring throughout. The lunar orbiter satellites took images of potential landing sites. In 1966, Lunar Orbiter 2 sent back this image of Copernicus crater, one of the first ever close-up views of the moon. Apollo riding his chariot across the sun was appropriate to the grand scale of the proposed program. Abe Silverstein. Earth's place in space. Apollo 8 was the first manned spacecraft to leave Earth's orbit. On Christmas Eve 1968, Frank Borman, James Lovell, and Bill Anders looped around the far side of the moon and witnessed the astounding sight of Earth rising from behind the moon's surface. For the first time, humans could see their home from space, a startlingly blue world lost in the immensity of the void. As Anders put it, "We came all this way to explore the moon, and the most important thing is that we discovered the Earth." The crew was also the first to pass through the Van Allen radiation belts. This zone of charged particles extends up to 15,000 miles from Earth, and was initially thought to be a serious barrier to human space travel. As it turned out, it resulted in a dosage of radiation only equivalent to a chest X-ray. Finally, the program was ready for the last step, to take real steps on the moon itself. On July 21, 1969, an estimated global audience of 500 million tuned in to watch Neil Armstrong land the lunar module and step out onto the surface of the moon, closely followed by Buzz Aldrin. It was the culmination of nearly a decade of collaborative effort and effectively ended the space race. There were 6 more missions to the moon following Apollo 11, including the near disaster of Apollo 13, whose lunar landing in 1970 was aborted after an oxygen tank exploded on board. The crew was returned safely to Earth on the crippled spacecraft in a real-life drama that played out in front of a worldwide television audience. In 1968, Apollo 8 broadcast live from moon orbit. Images taken from the spacecraft by astronaut Bill Anders included the iconic Earthrise. Learning about the moon. Before Apollo, much of what was known about the physical nature of Earth's only natural satellite was speculation, but, with the political goals achieved, here was an opportunity to find out about an alien world firsthand. Each of the 6 landing missions carried a kit of scientific tools, the Apollo Lunar Surface Experiments package. Apollo's instruments tested the internal structure of the moon, detecting seismic vibrations that would indicate a moonquake. Other experiments measured the moon's gravitational and magnetic fields, heat flow from its surface, and the composition and pressure of the lunar atmosphere. Thanks to Apollo, scientists have compelling evidence from analysis of moon rock that the moon was once a part of Earth. Like Earth, the moon also has internal layers and was most likely molten at some point in its early history. Unlike Earth, however, the moon has no liquid water. Since it has no moving geological plates, its surface is not continually repaved, and so the youngest moon rocks are the same age as Earth's oldest. The moon is not entirely geologically inactive, however, and occasionally has moonquakes that last for hours. One Apollo 11 experiment remains active and has been returning data since 1969. Reflectors planted on the lunar surface bounce back laser beams fired from Earth, enabling scientists to calculate the distance to the moon to within an accuracy of a couple of millimeters. This gives precise measurements of the moon's orbit, and the rate at which it is drifting away from Earth. Neil Armstrong took this famous photograph of Buzz Aldrin on the surface of the moon. Armstrong's reflection, standing next to the lunar module, can be seen in Aldrin's visor. Apollo's legacy. On December 19, 1972, the sonic boom over the South Pacific, as the Apollo 17 capsule thumped into Earth's atmosphere, sounded the end of the Apollo program. In total, 12 men had walked on the moon. At the time, it was widely assumed that routine flights to Mars would soon be a reality, but in the intervening 40 years, scientific priorities changed, politicians worried about costs, and human space travel has not ventured farther than Earth's orbit. For many, the decision to end manned moon missions was a wasted opportunity, caused by a lack of imagination and leadership. However, the end of the acute Cold War competition that gave rise to the Apollo program heralded a new era of international cooperation for NASA, with Skylab, Mir, and the International Space Station. Gene Cernan, the last man on the moon, predicted that it could be another 100 years before humankind appreciates the true significance of the Apollo missions. One result could be that it may have made the U.S. smarter. The intake for doctoral degrees at American universities tripled during the 1960s, particularly in the field of physics. Apollo contracts also nurtured nascent industries, such as computing and semiconductors. Several employees of the California-based Fairchild Semiconductors went on to found new companies, including Intel, a technology giant. The Santa Clara area where these firms were based has become today's Silicon Valley. But perhaps Apollo's real legacy is the idea of Earth as a fragile oasis of life in space. Photos taken from orbit, such as the Blue Marble and Earthrise, fed into a growing awareness of planet Earth as a single entity, and the need for careful stewardship. Apollo 11's command and service module docked with the lunar module in orbit before heading for the moon. Before touchdown, the service module was jettisoned, and only the command module returned to Earth. Houston. Tranquility Base here. The Eagle has landed. Neil Armstrong. On the final 3 Apollo missions, astronauts explored the surface of the moon on lunar rovers. The rovers were abandoned and can still be seen where they were left behind. Gene Kranz. Perhaps the embodiment of the NASA spirit is not the heroic astronauts but the legendary Apollo flight director Gene Kranz. Born in 1933, Kranz was fascinated by space from an early age. He served as a pilot with the U.S. Air Force before leaving to pursue rocket research with the McDonnell Aircraft Corporation and then NASA. Prominent and colorful, with a brutally close-cut flat-top hairstyle, Kranz was unmistakable in mission control, dressed in his dapper white mission vests made by his wife. Although he never actually spoke the words, "failure is not an option," they were written for his character in the movie Apollo 13, they sum up his attitude. Kranz's address to his flight control staff after the Apollo 1 disaster has gone down in history as a masterpiece of motivational speaking. In it, he stated the Kranz dictum, "tough and competent," that would guide mission control. Kranz was awarded the Presidential Medal of Freedom in 1970 for successfully returning Apollo 13 to Earth. See also, the launch of Sputnik, understanding comets, exploring Mars. In context. Key astronomer Viktor Safronov. Before 1755, German philosopher Immanuel Kant argues that the solar system formed out of a large gas cloud that collapsed. 1796, Pierre-Simon Laplace develops a model of solar system formation that is similar to Kant's. 1905, the American geologist Thomas Crowder Chamberlain first proposes that planets develop from particles that he calls planetesimals. After 1980s, several apparently young stars, such as Beta Pictoris, are found to be surrounded by disks of cool dust. 1983, the infrared astronomical satellite is launched. It observes that many stars have an excess of infrared radiation that could be explained if they were orbited by disks of cooler material. For centuries, astronomers have proposed various models to explain how the Sun and planets formed. During the 18th and 19th centuries, the nebular hypothesis came to prominence. This proposed that the solar system emerged from a giant cloud of gas and dust that collapsed and started rotating. Most of the material collected in the center, forming the Sun, while the rest flattened into a spinning disk of material from which the planets and smaller objects condensed. A version of this hypothesis was put forward by Frenchman Pierre-Simon Laplace in 1796. In the late 1960s, Viktor Safronov was working in Moscow on how planets could form in a nebula. He wrote an important paper in 1969, which was unknown outside the Soviet Union until an English version was published in 1972. Safronov's theory, which today is known as the solar nebular disk model, was essentially a modified, mathematically more fully formed version of the nebular hypothesis. Up to the 1940s, astronomers considered that the nebular hypothesis contained a major flaw known as the angular momentum problem. They calculated that if the solar system had formed out of a contracting, rotating cloud, the Sun should be spinning much faster than it actually is. During the first half of the 20th century, a number of alternative hypotheses competed with the nebular hypothesis. One suggested that planets might have formed from material pulled out of the Sun by a passing star, another that the Sun passed through a dense interstellar cloud and emerged enveloped in the gas and dust from which planets coalesced. Eventually, solid reasons emerged for rejecting these alternatives. Safronov's theory develops. Undeterred, Safronov studied in detail how planets might have formed in the disk of material proposed by Laplace. This disk would have consisted of a collection of dust grains, ice particles, and gas molecules, all orbiting the early Sun. Safronov's breakthrough came when he calculated the effect on such a system of some particles colliding. He figured out the speeds at which they would collide. Particles traveling at fast speeds would simply bounce off each other. But slower-moving particles would stick together, resulting in larger particles. As they grew bigger, the gravity of each particle would cause them to coalesce, forming larger objects called planetesimals. The larger objects would attract more mass, and the largest planetesimals would grow larger and larger, until they had gathered everything that lay within their gravitational reach. After a few million years, only a few planet-sized bodies would remain. By the 1980s, there was wide agreement over the SNDM. One researcher suggested that the angular momentum problem could be solved by dust grains in the original disk slowing down rotation in the center. Others incorporated Safronov's ideas into computer models, which suggested that systems of particles orbiting the early Sun could indeed have formed into a handful of planets. Recent observation of disks of cool dust surrounding apparently young stars lend further support to the SNDM. In Safronov's model, the planets formed out of dust and ice particles, which stuck together within a disk of material spinning around the newly formed Sun. Viktor Safronov. Viktor Sergeyevich Safronov was born in Veliky Luki near Moscow in 1917, and graduated from Moscow State University Department of Mechanics and Mathematics in 1941. In 1948, he obtained a doctorate degree. Safronov spent a considerable part of his career working at the Schmidt Institute of the Physics of the Earth, part of the Academy of Sciences in Moscow. There, he met his wife, Eugenia Ruskell, who for a time collaborated with him in his research. From the 1950s to the 1990s, he worked on modeling the idea that the planets formed within a disk of gas and dust. Today, Safronov's planetesimal hypothesis of planet formation is widely accepted, although alternative theories exist. After the fall of the Soviet Union in 1991, he had the opportunity to explain his ideas in the West. Key work: 1972 Evolution of the protoplanetary cloud and formation of the Earth. See also, Gravitational disturbances, the Kuiper belt, the Oort cloud inside giant molecular clouds. In context: key astronomer Ray Davis. Before 1930, Austrian physicist Wolfgang Pauli proposes the existence of neutrinos. 1939, Hans Bethe outlines two main processes by which stars obtain their energy. 1956, American physicists Clyde Cowan and Frederick Raynes confirm the existence of the antineutrino, the antiparticle of the neutrino. After 1989, the Kamiokande 2 experiment in Japan, organized by Masatoshi Koshiba, demonstrates conclusively that the Sun is a source of neutrinos and confirms Davis's abnormally low detection rate. During the first half of the 20th century, scientists figured out a process by which the Sun produces energy by fusing hydrogen into helium. In the Sun's core, 4 hydrogen nuclei, which are single protons, are changed into a helium nucleus, 2 positrons, and 2 tiny ghost-like particles called neutrinos, with the release of energy. The neutrinos produced were envisaged to escape easily from the Sun. Although this theory was accepted by the 1950s, it was not proven. In 1955, an American chemist named Ray Davis set out to show that the Sun produces energetic neutrinos by detecting just a few of them. He faced a huge problem in achieving this goal, however. Apart from the fact that their existence was uncertain, scientists thought that neutrinos had zero electric charge and a tiny mass, and very rarely interacted with other particles. If the Sun fuses hydrogen, scientists thought, billions of neutrinos should be passing through every square centimeter of Earth's surface every second, but perhaps only 1 in 100 billion might interact with atomic matter. Davis thought that neutrinos might be detectable through their involvement in a type of radioactive decay called beta decay. In theory, an energetic neutrino should be able to convert a neutron in an atomic nucleus into a proton. In his experiments, Davis found that, on very rare occasions, a neutrino passing through a tank of a chlorine-containing substance would interact with the nucleus of a stable chlorine atom to produce a nucleus of an unstable isotope of argon called argon-87. Neutrino physics is largely an art of learning a great deal by observing nothing. Chaim Harari, Israeli physicist. Homestake experiment. In 1964, in what was called the Homestake experiment, Davis began a trial using a large tank of a chlorine-containing chemical as a detector. An acquaintance of Davis, astrophysicist John Bacall, calculated the theoretical number of neutrinos of different energies that the Sun should be producing and, from this, the rate at which argon-37 should be produced in the tank. Davis began counting the actual numbers of argon-37 atoms produced. Although Davis's experiment showed conclusively that the Sun does produce neutrinos, only about 1/3 of the number of argon-37 atoms predicted by Bacall were detected. The discrepancy between the number of neutrino interactions predicted and those detected became known as the solar neutrino problem. Building on his 1989 work, In 1999, Masatoshi Koshiba discovered the cause of the discrepancy at Japan's huge Super Kamiokande neutrino detector. Neutrinos were found to oscillate between three different types: the electron neutrino, the muon neutrino, and the tau neutrino, while traveling through space. Davis's experiment had detected only the electron neutrinos. Davis's neutrino detector was placed deep underground to protect it from cosmic rays. Ray Davis. Raymond Davis was born in Washington, D.C., in 1914. He earned a Ph.D. in physical chemistry from Yale University in 1943. Davis spent the later years of World War II in Utah, observing the results of chemical weapons tests. From 1946, he worked at a laboratory in Ohio, carrying out research on radioactive chemical elements. In 1948, he joined Brookhaven National Laboratory, on Long Island, which was dedicated to finding peaceful uses for nuclear power. He spent the rest of his career studying neutrinos. Davis retired from Brookhaven in 1984, but continued his involvement in the homestake experiment until it ended in the late 1990s. Davis met his wife, Anna, at Brookhaven Laboratory, and together they had 5 children. He shared the Nobel Prize in Physics in 2002 with Masatoshi Koshiba for pioneering contributions to astrophysics. He died in Blue Point, New York, age 91 in 2006. Key work: 1964 Solar Neutrinos 2, Experimental. See also, Cosmic Rays Energy Generation Gravitational Waves. In context: Key astronomers Louise Webster, Paul Merton, Tom Bolton. Before 1783 English clergyman John Michell suggests the existence of a star whose gravity is so strong that not even light can escape it. 1964 Cosmic X-rays are detected by Geiger counters in sounding rockets. 1970 Uhuru, the first X-ray observatory satellite, is launched. After 1975 Stephen Hawking makes a bet with theoretical physicist Kip Thorne that Cygnus X1 is not a black hole. 1990 Hawking concedes the bet and buys Thorne a subscription to Penthouse magazine. 2011 further observations give Cygnus X1 an expected mass of 14.8 suns. Black holes are invisible. They allow no matter to escape, and, with the exception of low-level Hawking radiation at the event horizon, even swallow up electromagnetic light energy. Due to the difficulty of detecting an invisible object, black holes remained purely theoretical concepts up to the mid-20th century. However, such a concentrated mass ought still to create observable effects. As it is dragged into a black hole, matter will be heated to millions of degrees as it is ripped apart by gravitational forces, pouring out X-rays into space in the process. In the 1960s, astronomers looked for cosmic X-ray sources with a series of balloon and rocket launch detectors. Many of the hundreds of sources that they found were assumed to be X-ray binaries, star systems in which a superdense stellar remnant, such as a neutron star, tears material away from its visible companion. Among the first of these X-ray binaries to be discovered, in 1964, was a strong source close to active star-forming regions of the Milky Way, in the constellation of Cygnus. In 1973, Australian Louise Webster, Britain, Paul Merton, and American Tom Bolton independently took measurements of the blue supergiant star HDE 226868. They revealed that it orbits an object far too massive to be a neutron star. The only candidate for the invisible partner, Cygnus X1, was a black hole. Black holes were now more than mere theoretical entities. An artist's impression shows matter flowing from the blue supergiant star HDE 226868 into its black hole partner, Cygnus X1. The star is losing one solar mass of material every 400,000 years. See also, supernovae, cosmic radiation, Hawking radiation. In context: Key astronomer Stephen Hawking. Before 1916 Karl Schwarzschild provides a solution to the field equations of general relativity, allowing him to describe the gravitational field around a black hole-like object. 1963 New Zealand mathematician Roy Kerr describes the properties of a rotating singularity. 1965 British mathematician Roger Penrose shows that the gravitational collapse of a giant star could result in a singularity. 1967 American physicist John Wheeler coins the term black hole for the types of objects described by Schwarzschild, Kerr, Penrose, and others. After 2004 Stephen Hawking retracts an earlier claim that any object entering a black hole is completely lost to the universe. The mathematical theory of black holes was pioneered in the 1910s by the German physicist Karl Schwarzschild. The object described by Schwarzschild was a non-rotating mass concentrated at a point of infinite density, called a singularity. At a distance from this, known as the Schwarzschild radius, was an imaginary spherical surface called the event horizon. The gravity on the singularity side of this surface was so great that nothing, not even light, could escape. In subsequent decades, black hole theory evolved in various ways, but black holes continued to be regarded as entirely black, emitting no light. Virtual particles. In 1974, a big change occurred in black hole theory. British physicist Stephen Hawking proposed that black holes emit particles, known today as Hawking radiation. Hawking maintained that black holes are not completely black, since they emit radiation of some sort, if not necessarily light. Quantum theory predicts that, throughout space, pairs of virtual particles and their antiparticles should continually appear out of nothing, then annihilate. One of each pair has positive energy, the other negative energy. Some of these particle-antiparticle pairs will appear just outside the event horizon of a black hole. It is possible that one member of the pair could escape, observed as an emission of radiation energy, while the other falls into the black hole. In order to preserve the same total energy in the system, the particle that fell into the black hole must have had negative energy. This causes the black hole to slowly lose mass energy, a process called black hole evaporation. Hawking radiation remains a theoretical prediction. If it proves correct, it means that black holes do not last forever, which has implications regarding the fate of the universe, since it had been thought that black holes would be among the last objects in existence. See also, Curves in Spacetime, the Life Cycles of Stars, the Heart of the Milky Way. Michel. Introduction. Most major discoveries in astronomy have been made possible by advances in technology. Recent developments have provided powerful tools to collect radiation from space and to process vast amounts of data, and the pace of discovery has accelerated at a breathtaking rate. Microelectronics and computing capability, in particular, have opened up new possibilities over the last 40 years. Telescopes and detectors. The New Technology Telescope opened by the European Southern Observatory in the Chilean Andes in 1989 is an example of a telescope with revolutionary innovations that have subsequently become standard equipment. Its main and secondary mirrors are flexible, but kept precisely in shape by a network of computer-controlled supports called actuators. ESO's choice of Chile was part of the trend for astronomers to scour the world, testing for the best sites where the air is clear, still, and dry, and the sky free from light pollution. Another major center for astronomy was established at the summit of the volcano Mauna Kea on the Big Island of Hawaii in 1967. This prime site is now home to 13 telescopes. Until the early 1970s, all astronomical imaging was carried out by means of conventional photography. Then, in the mid-1970s, a completely new way of recording an image electronically became a practical reality. This was the charge-coupled device. CCDs are electronic circuits with light-sensitive pixels that generate electrical charges when light photons land on them. They are far superior to photography for sensing faint light and recording an object's brightness accurately, and they made visible objects that had previously been too faint to detect, such as the small, icy worlds of the Kuiper belt beyond Neptune. We're going to need a definitive quantum theory of gravity, which is part of a grand unified theory. It's the main missing piece. Kip Thorne. Computing power. Fast, reliable computers and an immense capacity for storing data have been key not only to the way that telescopes and their instruments are constructed, but also to making sense of the astronomical data they collect. One major project alone, the Sloan Digital Sky Survey, has collected information about 500 million celestial objects since it began in 2000. This database has been used to create a three-dimensional map showing how galaxies are distributed across the universe, revealing its largest structures. Computers are indispensable to theorists, too. Huge computing power makes it possible to gain insight into what observations are telling us about the way the universe works by creating simulations based on the laws of physics. For example, computers allow scientists to model ways in which the solar system may have formed and evolved. Space exploration has now pushed right out to the edge of the solar system, and no region of the planetary system remains unexplored on some level. The New Horizons mission passed Pluto in 2015 and is moving through the Kuiper Belt, while the Voyager spacecraft, launched back in 1977, are now sending back data from interstellar space. With the advent of the Internet, missions can also be followed in real time, as the latest images from the Hubble Space Telescope or the Curiosity rover on Mars are made instantly available. Landmark discoveries. Of the many discoveries in recent decades that have had an impact on our understanding, three stand out. The surprise finding in 1998 that the universe's expansion is accelerating showed that there is a gap in fundamental theory. By contrast, the detection of gravitational waves in 2016 confirmed Einstein's 100-year-old theoretical prediction. Meanwhile, the discovery of the first extrasolar planet in 1995, and thousands more since, has energized the search for alien life. It is impossible even to speculate where the next 20 years may lead. In context. Key organization. NASA, Voyager mission before. 1962 Mariner 2 passes Venus in the first planetary flyby. 1965 Mariner 4 is the first craft to visit Mars. 1970 Venera 7 makes the first soft landing on Venus. 1973 Pioneer 10 is the first spacecraft to cross the asteroid belt en route to Jupiter. 1976 Viking 1 sends pictures from the surface of Mars. After 1995 the Galileo spacecraft goes into orbit around Jupiter. 1997 Sojourner is the first rover to land on Mars. 2005 the Cassini orbiter releases the Huygens probe, which touches down on Titan. 2015 New Horizons makes the first flyby of Pluto and Charon. On August 20, 1977, the Voyager 2 spacecraft was launched from Cape Canaveral in Florida. 2 weeks later, its sister craft Voyager 1 was launched. Thus began the most ambitious exploration of the solar system ever. The launch was the culmination of more than a decade's work. The core mission would run for 12 years, but an interstellar mission continues. A Titan IIIe rocket lifts off carrying the Voyager 1 spacecraft as its payload. The Titan IIIe was the most powerful launch vehicle of its time. Going interplanetary. By the early 1960s, both the Soviet and US space agencies were sending missions to other planets. There were more failures than successes, but over the decade robotic spacecraft began sending back close-up images of Venus and Mars. The NASA craft were part of the Mariner program, run largely from the Jet Propulsion Laboratory in California. The mathematicians at JPL perfected the art of the flyby, sending a spacecraft on a trajectory that had it fly past a planet close enough to photograph and observe it, albeit too quickly to enter its orbit. In 1965, a graduate student named Gary Flandreau, who was working at JPL for the summer, was given the task of figuring out routes to the outer planets and discovered that, in 1978, all the outer planets would be on the same side of the Sun. His calculations revealed that this had not happened since 1801, and would not occur again until 2153. Flandreau saw the opportunity for a grand tour of the outer solar system, but the distances involved were far beyond the capabilities of the spacecraft of the day. In 1965, Mars's alignment made it the closest planet to Earth at that time at 35 million miles, but Neptune was 2.5 billion miles away, and a journey to it would take several years. Planetary slingshots. A Grand Tour spacecraft would have to change course several times in order to fly past all its planets. Flandreau's plan had to use gravity assists to fling the craft from planet to planet. Also known as a gravitational slingshot or swing-by, a gravity assist had first been used by the Soviet Luna 3, which had swung around the far side of the Moon in 1959. Photographing as it went. It had never been used to guide spacecraft as far from Earth as the outer planets. The planned slingshot required the craft to approach the planet head-on, traveling in the opposite direction from the planet's orbital motion. The planet's gravity would speed up the craft as it made a loop around the planet. It would then slow down again as it headed off into space, having done an about turn. If the motion of the planet were ignored, the craft's escape speed would be more or less equal to its approach speed. However, taking the motion of the planet into account, the craft would leave the planet having added approximately twice the speed of the planet to its own velocity. A slingshot would not only redirect the craft, but also accelerate it on to its next target. It was a chance that came around once in every 176 years, and we prepared for it. Out of that emerged the greatest mission of planetary exploration to this day. Charles Colhay's. An artist's impression shows Voyager 1 in space. This craft and its twin, Voyager 2, communicate with Earth via radio waves transmitted and received by a 12-foot dish. Taking a grand tour. In 1968, NASA set up the Outer Planets Working Group. It proposed the Planetary Grand Tour mission, which would send one spacecraft to visit Jupiter, Saturn, and Pluto, and a second one toward Uranus and Neptune. The plan required a new long-range spacecraft and costs grew steadily. Then in 1971, NASA canceled the Grand Tour as it needed cash to fund the Space Shuttle program. The exploration of the outer planets was handed back to the Mariner program. The mission was named Mariner Jupiter, Saturn, or MJS-77 for short. 77 referred to the launch year. To reduce costs, Pluto was removed from the tour itinerary. Instead, one craft was to visit Jupiter, Saturn, and finally Saturn's huge moon Titan. Titan was considered more intriguing than distant Pluto. It was larger than Mercury, and thought at the time to be the largest moon in the solar system. It was also the only moon known to have its own atmosphere. This change meant that the mission would be budgeted as an exploration of the two gas giants, not a grand tour. However, the spacecraft, codenamed JST, was to have a backup, JSX. Its mission would also include Jupiter and Saturn if JST failed. The X represented an unknown quantity. If required, JSX would go to Titan, but if JST achieved its mission, then JSX would be sent to Uranus and Neptune. Jupiter's moon Europa was photographed by Voyager 2. It is covered in a thick crust of ice, which has been fractured and filled in with material from the moon's interior. Mission profile. In 1974, mission design manager Charles Colhay began to make a master plan for the MJS-77 mission. He had to consider every aspect, from the spacecraft's design, size, and launch system to the many variables they would encounter along their routes, the radiation levels, light conditions, and contingencies for altering the missions. It took Colhay and his team 8 months to eventually settle on 2 trajectories that met all the criteria and would take the spacecraft as close to as many points of interest as possible. Neither Colhay nor anyone else working on MSJ-77 liked the name. As the launch date approached, a competition for a new name was organized. Nomad and Pilgrim made the shortlist, but by the time the 2 identical spacecraft were ready, they were known as Voyager 1 and Voyager 2. At 1,590 pounds, the 2 Voyager spacecrafts were nearly 50% heavier than any previous flyby craft. About 220 pounds of that was scientific equipment, comprising 2 cameras, magnetic field sensors, spectrometers that would analyze light and other radiation to show which chemicals were present in atmospheres, and particle detectors for investigating cosmic rays. In addition, the radio system could be used for a variety of experiments, such as probing atmospheres and Saturn's rings. The spacecraft's trajectories were to be controlled by 16 hydrazine thrusters. However, it would be too dark beyond the asteroid belt for solar panels to generate enough electricity for the spacecraft, and batteries would not last nearly long enough. The answer was nuclear power in the form of radioisotope thermoelectric generators, held out on a boom to isolate them from sensitive equipment. Each RTG contained 24 balls of plutonium that gave out heat, which was converted into an electric current by thermocouples. The power supply was built to last for nearly 50 years. Voyager 1 captured a 100-mile-high eruption on Jupiter's moon Io. Strongly affected by Jupiter's gravity, Io is the most volcanically active place in the solar system. Jupiter and its moons. By December 1977, Voyager 1 had overtaken Voyager 2, which was taking a more circular trajectory. It reached the Jupiter system in January 1978. Most of Voyager 1's important discoveries were made in a frenetic 48-hour period around March 5, when it made its closest approach, coming within 217,000 miles of the planet's cloud tops. In addition to sending back images, Voyager 1 analyzed the compositions of the clouds and measured the planet's immense magnetic field. It also showed that Jupiter had a faint ring system. Its most memorable discoveries came from the flybys of the Galilean moons. These were not sparse, cratered balls but active worlds. Photographs of Io showed the largest volcanic eruptions ever seen, spurting ash clouds into orbit. Fresh measurements of Ganymede revealed that it superseded even Titan in size, while images of Europa's eerily smooth yellowish disk had astronomers puzzled. Voyager 2 arrived at Jupiter more than a year later, and did not approach as close as Voyager 1, but it took some of the mission's most iconic images of Io transiting Jupiter. Voyager 2 also got a closer look at Europa, showing that it was covered in a crust of water ice riven by cracks. Later analysis revealed that these cracks were caused by upwellings in a liquid ocean under the crust, an ocean that is estimated to hold at least twice as much water as Earth and which is thought by scientists to be a prime candidate for the presence of alien life. The latter half of the next decade abounds in interesting multiple planet opportunities. Of particular interest is the 1978 Grand Tour, which would make possible close-up observation of all planets of the outer solar system. Gary Flandreau. Voyager 2's images of Saturn's rings revealed a complex structure made of small satellites, none of which were larger than 3.6 miles across. Titan and Saturn. By November 12, 1980, Voyager 1 was skimming 77,000 miles above the atmosphere of Saturn. On the approach, and despite some instrument failures, it revealed details of the rings, which were made of billions of chunks of water ice and were as thin as 30 feet in places. Kohlhase had sent Voyager 1 to visit Titan before approaching Saturn to prevent any damage caused by Saturn's atmosphere and rings from endangering this crucial phase. The spacecraft swung behind Titan so the sun's light shone through the atmosphere, allowing measurements of its thickness and composition. The Titan trajectory then sent the craft over Saturn's pole and away to the edge of the solar system. Voyager 2 arrived at Saturn in August 1981, and was able to study the planet's rings and atmosphere in more detail, but its camera failed during much of the flyby. Fortunately, it was restored, and the order was given to continue to the ice giants. Voyager 2 sent back this image of Neptune's ice moon Triton. During the craft's flyby, only the southern ice cap was visible. Highly reflective, it is made of frozen nitrogen and methane. Uranus and Neptune. Voyager 2 is the only craft to have visited the ice giants Uranus and Neptune. It took 4.5 years to travel from Saturn to Uranus, where the craft passed 50,500 miles above the pale blue atmosphere. It looked at the planet's thin rings and discovered 11 new moons, all of which are now named after Shakespearean characters, as is the rule for Uranus. The most curious thing to be examined on this otherwise relatively quiet planet is the tilt of its axis, which is roughly 90 degrees. As a result, Uranus does not spin as it orbits, but rolls around the Sun. The final port of call was Neptune, reached in August 1989. This deep blue planet was found to have the strongest winds in the solar system, up to 1,500 miles per hour, 9 times stronger than anything experienced on Earth. The Voyager's mission controllers were able to abandon caution as the planetary mission drew to an end. Without regard for the safety of its final trajectory, Voyager 2 was redirected to fly past Neptune's moon Triton. The images of the huge ice moon showed geysers blasting fountains of slush from the surface. The golden records carried by the Voyager spacecraft included a selection of music, greetings in 55 different languages, and images of humans, animals, and plants. Continuing mission. The Voyager program continues and the two craft are still in touch with NASA. As of 2016, Voyager 1 was 12.5 billion miles and Voyager 2 was 10 billion miles away. 6 times a year, the craft spin around to measure the cosmic rays around them. This data shows that the craft are approaching the edge of the heliosphere, the region of space that is influenced by the Sun. Soon they will enter interstellar space and measure the cosmic wind from ancient stellar explosions. In 2025, the two spacecraft will power down and go quiet forever, but their mission may still not yet be complete. A committee chaired by Carl Sagan selected content for a gold-plated phonograph record. They included greetings from the world, the sounds and sights of Earth, and even human brain waves. The record is a calling card from humankind to an alien civilization. The Voyagers are not heading for any star systems. The closest they will get is when Voyager 1 passes 1.6 light-years from a star in 40,000 years' time. In all likelihood, they will never be found by intelligent life, but the golden records are a symbol of the hope with which the two interplanetary spacecraft were sent on their way. The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. Carl Sagan. By 2005, the Voyagers had reached the termination shock, where the solar wind slows and becomes turbulent as it mixes with the interstellar medium, entering the heliosheath region. By 2016, they were nearing the heliopause, where the solar wind is stopped by the interstellar medium. Charles Kohlhase. Charlie Kohlhase was born in Knoxville, Tennessee, and graduated with a degree in physics. He briefly served in the U.S. Navy before joining JPL in 1960, where he turned his lifelong fascination with exploration into work on the Mariner and Viking projects, before joining the Voyager team. In 1997, Kohlhase left Voyager to design the Cassini-Huygens mission to Saturn, which succeeded in dropping a lander onto the surface of Titan in 2005. In the late 1970s, he worked with computer artists to create accurate animations of space missions for advancing the public understanding of NASA's work.
Now retired, Kohlhase remains involved in several projects that blend art and space science, aiming to educate and inspire the next generation of rocket scientists and interplanetary explorers. Key work: 1989 The Voyager Neptune Travel Guide. See also, Life on Other Planets, The Nebular Hypothesis, Exoplanets, Understanding Comets, Studying Pluto. In context. Key astronomer Vera Rubin. Before 1925 Bertil Lindblad calculates the likely shape of the Milky Way. 1932 Jan Urdt finds that the rotational speeds of the Milky Way galaxy do not match the presumed mass. 1933 Fritz Zwicky suggests that a majority of the universe is made up of dark, invisible matter. After 1999 it is discovered that dark energy is accelerating the expansion of the universe. 2016 The LIGO experiment detects gravitational waves, which offer a new method to map the distribution of dark matter across the universe. Isaac Newton's universal law of gravitation is adequate for making calculations to launch a satellite into orbit, land a crew on the moon, and send a spacecraft on a grand tour of the planets. Newton's clear mathematics works well enough for most things on the solar system scale, but not on grander scales of the universe, where Einstein's relativistic theory of gravity is needed. Nevertheless, Newton's law of gravitation was all that was required to reveal one of the biggest, and as yet unsolved, mysteries of astronomy, dark matter. In 1980, American astronomer Vera Rubin presented clear evidence that dark matter exists. Thanks to Rubin, the general public learned that most of the universe appears to be missing. Throughout the 1960s and 1970s, the science of astronomy was dominated by projects on a grand scale, as researchers used massive instruments, often in remote parts of the world, to search for exotic objects, such as black holes, pulsars, or quasars. By contrast, Rubin was looking for a research area that would allow her to stay in her home city of Washington, D.C., and raise her 4 children. She chose to study the rotation of galaxies, specifically looking at the anomalous behavior of the outer regions of galaxies. We became astronomers thinking we were studying the universe, and now we learn that we are just studying the 5% that is luminous. Vera Rubin. Spinning spirals. The problem Rubin tackled was the fact that huge disks of stars in nearby galaxies did not move in a way that was consistent with Newton's law of gravity. Their outer regions moved too quickly. This curiosity was not new, but it had previously been largely ignored. Since the 1920s, when Bertil Lindblad and others showed that the Milky Way, and by extension many other galaxies, were disks of stars moving around a central point, it was assumed that galaxies were orbital systems just like any other. In the solar system, near objects orbit at a faster speed than distant ones, so Mercury is moving much more rapidly than Neptune. This is because, following Newton, gravity decreases with a square of the distance. When the velocities of the planets are plotted against their distance from the Sun, the data forms a smooth downward rotation curve. It followed that plotting the orbital speeds of stars at different distances from the galactic center should produce a similar curve. In 1932, Dutch astronomer Jan Oort was the first person to provide observational proof that the galaxy was a single orbital system made up of a swirling spiral of stars, in which the Sun completed a 225 million-year orbit. However, in the course of his calculations, Oort found that the motion of the galaxy suggested that it was twice as massive as the total mass of visible stars. He concluded that there must be some hidden source of mass. A year later, the Swiss-American Fritz Zwicky was studying the relative motion of galaxies in the Coma cluster. He found, again, that their motion suggested the mass of what could be seen was not the only stuff there. He named the missing material Dunkelmaterie or dark matter. Oort's early measurements were inaccurate, while Zwicky's initial assessment was that dark matter was 400 times more abundant than the matter of visible material, a huge overestimate. This meant that their findings were dismissed as measurement errors. In 1939, American Horace Babcock again found anomalies in the rotation of Andromeda and suggested that there was some mechanism by which light from the missing matter was being absorbed in the galactic core. Galactic rotation curve. More than 20 years later, Rubin returned to the problem of galactic rotation. Like Babcock, she chose to focus on the rotation of the Andromeda galaxy, the Milky Way's nearest galactic neighbor. She worked with her colleague Kent Ford at the Carnegie Institution at Washington to measure the velocities of objects in the outer region of the galaxy. They did this using a sensitive spectrograph, which allowed them to detect the redshift and blueshift of objects, and calculate their relative speeds away from and toward Earth. After several years of slow but careful work, Rubin had enough data to plot a rotation curve for the galaxy. Instead of swooping downward like the curve of the solar system, the speed data of the galactic curve stayed relatively level with distance. This meant that the outer regions of Andromeda were moving at the same speed as the areas nearer to the center. If the galaxy's mass was limited to what could be observed using telescopes, the outer regions of Andromeda would be moving faster than escape velocity, and they should simply fly off into space. However, they were clearly being held in place by the galaxy's overall mass. Rubin calculated that the total galactic mass required to hold the outer regions in orbit was about 7 times greater than the visible mass. The ratio of matter to dark matter is today thought to be around 1:6. In the absence of dark matter, the velocities of objects in the outer regions of galaxies would be slower than the observed values. Here, the observed rotation curve is plotted against the expected curve from visible matter alone. What is dark matter? Rubin's galactic rotation curve, widely disseminated in 1980, was the visual proof that dark matter existed. As further evidence mounted, the mystery as to what it might be remained. Dark matter cannot directly be observed. Only its effects are detectable, and the only effects that can be detected are from its gravity. It does not interact with the electromagnetic force, meaning that it does not absorb heat, light, or other radiation, nor does it emit any. Dark matter may be completely invisible. No observational problem will not be solved by more data. Vera Rubin. Dark matter could be evidence that the universe is one of many that exist next to one another, in separate spatial dimensions, in a bubble-like multiverse. Possible sources. The simplest solution to the dark matter problem is the most literal. It comprises ultradense bodies of ordinary matter that are too dark to observe. Astronomers have dubbed these machos, which stands for massive compact halo objects. Machos include objects like black holes, neutron stars, and white and brown dwarfs. They occupy the galactic halo, a dark and diffuse region that surrounds the main, shining disk of a galaxy, and this is why it is difficult to see them. Machos are clearly out there, but by current estimates they would only account for a tiny proportion of dark matter. An alternative idea is the WIMP, weakly interacting massive particle. This concept is based largely on an idea in particle physics called supersymmetry. It proposes a new explanation of energy and ordinary matter. Energy and matter form two distinct groups of subatomic particles, and supersymmetry proposes that these groups interact thanks to the actions of superparticles, or sparticles. Dark matter WIMPs might be sparticles that escaped from their partners in the early period of the universe, or they may be objects that are there all along. Finally, dark matter might be the observable effect of another universe, or perhaps several, that exist in a spatial dimension different from this universe. Their matter could be very close, a few centimeters away, but because the radiation from each universe is trapped inside its own spacetime, one universe can never see another. However, the gravitational effects of the matter in the hidden universes leaks through into this one through the warping of spacetime. Providing an explanation for dark matter remains one of the biggest prizes in astronomy. However, in 1999, a possibly even more puzzling phenomenon was uncovered. It was discovered that 68% of the universe was neither matter nor dark matter, but so-called dark energy. Dark matter makes up 27%. Visible matter comprises a mere 5%. For the moment we might very well call them Dunos. Bill Bryson. A huge ring of dark matter, which formed long ago in the collision between two massive galaxy clusters, is shown around the edge of this Hubble Space Telescope image in lighter blue. Vera Rubin. Born Vera Cooper in Philadelphia, Rubin earned her first degree from Vassar College in upstate New York, and then applied to go to Princeton. Her application was ignored because women were barred from joining the university's graduate astronomy program until 1975. Instead, Rubin pursued her studies at Cornell University, where she studied under greats such as Richard Feynman and Hans Bethe. She subsequently earned a Ph.D. from Georgetown University in Washington, D.C., supervised by George Gamow. Her thesis, published in 1954, concluded that galaxies would clump together, a fact that was not fully explored until the work of John Huttray in the late 1970s. After teaching at a college in Maryland, Rubin returned to Georgetown, and then moved to the Carnegie Institution at Washington in 1965. It was here that she conducted her work on galactic rotation, and she has remained there ever since. Key work. 1997 Bright Galaxies, Dark Matters. See also, Gravitational Theory. Gravitational disturbance is the shape of the Milky Way supernovae, the Oort cloud. Dark energy. In context. Key astronomer Alan Guth. Before 1927 George Lemaitre proposes that the universe arose from a single primordial atom. This is later named the Big Bang Theory. 1947 George Gamow and Ralph Alpher describe how the elements hydrogen and helium were formed in the early universe. 1964 The cosmic microwave background is discovered to be a remnant of the Big Bang. After 1999 Dark energy is found to be accelerating the expansion of the universe. 2014 BICEP2 withdraws claims of finding evidence of inflation. 2016 LIGO detects gravitational waves, offering a new way to observe the structure of spacetime. By the 1970s, cosmologists were grappling with a variety of puzzles thrown up by the Big Bang Theory. In an attempt to solve them, Alan Guth proposed a stage of rapid inflation in the early universe, caused by the effects predicted by quantum theory. The puzzles. One of the problems with the Big Bang theory came from the grand unified theory, which describes how the forces of the universe arose a fraction of a second after the Big Bang. The gut predicted that high temperatures at this time would create bizarre features, such as so-called magnetic monopoles. There are, however, none to be found, which suggests the universe cooled faster than expected. A second problem arose from the way space is amazingly flat, meaning that it expands according to normal Euclidean geometry. A flat universe would only have arisen if the density of the early universe matched a certain critical figure. Varying it slightly one way or the other would have resulted in curved universes. The final issue was the horizon problem. Light from the edge of the observable universe has taken the entire life of the universe to reach Earth. As light speed is constant, scientists know that it has not had time to shine to the opposite edge of the universe. So if no light, energy, or matter has ever passed between the edges of the universe, this leaves a puzzle as to why space appears so similar in every direction. The solution. Guth's theoretical solution to these problems was to inflate the early universe using a quantum effect called a false vacuum, where positive matter energy was created as space expanded, equally balanced by an increase in gravity. In the first 35 seconds after the Big Bang, space doubled in size 100 times over, going from a billionth of the size of a subatomic particle to the size of a marble. This means that, at the very beginning, the edges were close enough to mix and become uniform, thus solving the horizon problem. During inflation, space expanded faster than the speed of light. The inflation cooled the universe rapidly, thus solving the gut problem, and locked in the uniformity seen today. Finally, the inflation ended as the density of the universe evened out at a value needed for a flat universe. In 2014, BICEP2, an experiment at the South Pole, reported ripples in space consistent with cosmic inflation. However, the claim was soon withdrawn. Cosmic inflation remains unproven, but it is the best current theory for the Big Bang. The recent developments in cosmology strongly suggest that the universe may be the ultimate free lunch. Alan Guth. It is not possible to visualize warped three-dimensional space, but if one dimension were removed, the geometry of space could be shown as curved, said L-shaped, and flat, where a triangle with angles of 180 degrees would be drawn. Alan Guth. Born in New Jersey, Alan Guth received his doctorate in 1972 and specialized in particle physics, pursuing research into quarks. By the late 1970s, he had worked at MIT, Princeton, Columbia, Cornell, and Stanford, as he searched the country for a long-term academic position. While at Columbia, Guth became interested in the grand unified theory, which had been proposed in 1974. He began developing his inflation theory in 1978 while at Cornell, after hearing about the problem of the flatness of the universe, and shortly afterward, the problems associated with gut. While at Stanford, he then came across the horizon problem, and went on to publish his famous theory in 1981. He is now a professor at MIT, where he helps with the search for evidence of cosmic inflation. Key works. 1997 The Inflationary Universe, The Quest for a New Theory of Cosmic Origins. 2002 Inflation and the New Era of High-Precision Cosmology. See also, The Birth of the Universe, the Primeval Atom Searching for the Big Bang Gravitational Waves. In context. Key astronomers Margaret Geller, John Huchard. 1842 Christian Doppler describes how wavelengths can change due to relative motion. 1912 Vesto Slipher discovers that galaxies are redshifted by the Doppler effect. 1929 Edwin Hubble uses redshift to show that distant galaxies are moving away faster than nearer ones. 1980 Alan Guth proposes that a rapid expansion, called cosmic inflation, shaped the universe. After 1998 the Sloan Digital Sky Survey finds walls, galaxy sheets, and filaments many hundreds of light-years long. 1999 a redshift survey of supernovae reveals that the universe's expansion is speeding up. Since the 1920s, The study of the redshift of distant galaxies has revealed the scale of space and the way in which the universe is expanding in all directions. Redshift occurs when a light source is moving away from the observer. In the 1980s, redshift surveys made by American astronomers Margaret Geller and John Huchra, working at the Harvard-Smithsonian Center for Astrophysics, gave an even clearer picture of the universe, showing that galaxies cluster around great voids of empty space. Geller and Huchra's work provided valuable clues to the nature of the very early universe. A redshift survey uses a wide-angle telescope to select target galaxies, generally millions of light-years away. Astronomers compare the light from each galaxy with benchmark wavelengths to determine the redshift, and thus the distance the light has traveled, allowing them to plot the positions of many galaxies. Huchra started the first redshift survey in 1977. By its completion in 1982, he had mapped 2,200 galaxies. Before Huchra began his survey, it was known that galaxies existed in clusters. For example, the Milky Way is one of at least 54 galaxies in a cluster called the Local Group, which is about 10 million light-years wide. It was assumed that clusters were evenly spread. However, by 1980, Huchra had shown through his redshift survey that dozens of clusters form superclusters hundreds of millions of light-years wide. The Local Group is part of the Laniakea supercluster, which contains 100,000 other galaxies. Walls of galaxies. In 1985, Geller began the KF2 redshift survey, taking 10 years to map 15,000 galaxies. Her survey confirmed that superclusters were themselves arranged in sheets and walls enclosing vast voids, like the surface film of a bubble. She found the first Great Wall of galactic superclusters in 1989. The exact size of KF2 Great Wall is still unclear, but it is estimated at 700 million light-years long, 250 million wide, and 16 million thick. It was the first of several supersized structures now known. The size of the voids puzzled astronomers. They were too large to have been emptied completely by the gravitational collapse of material that formed the stars and galaxies, which meant that they must have been empty since the beginning of the universe. Cosmologists theorized that the large-scale order of superclusters and voids is the legacy of quantum fluctuations during the inflationary epoch of the universe. Quantum fluctuations are fleeting changes in the amount of energy at points in space. These small but highly significant irregularities were locked into the fabric of the universe in the first fraction of a second of its existence, and remain today. They are now the vast areas of void permeated by a tangled pattern of matter. This computer simulation of a portion of the universe shows the distribution of 10,000 galaxies, which cluster in long filaments and walls, in between vast empty voids. Margaret Geller. Margaret Geller earned a Ph.D. from Princeton in 1975, and took various fellowships before joining the Harvard-Smithsonian Center for Astrophysics in 1983. She worked there with John Huchra, analyzing the results of his redshift survey. Geller went on to lead the second redshift survey. She is a frequent public speaker and has made several films about the universe, including Where the Galaxies Are, which takes viewers on a graphical voyage around the large-scale objects of the observed universe. See also, Spiral Galaxies Beyond the Milky Way Cosmic Inflation, a digital view of the skies. In context. Key astronomer Frank Hsu. Before 1947, Bart Bok observes dark nebulae and suggests that they are sites of star formation. 1966, Frank Hsu and Chia Chow-Lin developed the density wave theory to explain spiral arms in the Milky Way. After 2003, the Spitzer Space Telescope, an infrared observatory, is launched. It produces the best view yet of stellar nurseries. 2018, first light on the James Webb Space Telescope will allow astronomers to study protostars inside dark Bok globules. Stars form inside dark globules of dust and gas that are called giant molecular clouds. However, the process by which a cloud of gas transforms into an embryonic star, or protostar, has never been observed, partly because the process must take millions of years, and partly because even the most advanced telescopes find it difficult to penetrate the dark density of the cloud. Without observational evidence, astrophysicists must construct mathematical models for what they think is happening inside those dark globules. The most consistent model of star formation was derived by U.S. mathematician Frank Hsu. Hsu and his colleagues Fred Adams and Susanna Lozano at the University of California at Berkeley presented their model in 1986 after 20 years of work. The pillars of creation are vast clouds of gas and dust where new stars are made. This famous image was captured by the Hubble Space Telescope in 1995. The inside-out model. Hsu's system is called the singular isothermal model, or the inside-out model. It is built from the complex mathematics that define the dynamics of gas clouds, taking into account factors such as temperature, density, electrical charge, and magnetism. Hsu's model works by making the process self-similar. A starting condition that causes some of the gas cloud to contract into a dense core will result in the same, or similar, conditions, which cause more gas to join the core, and so on. This process was found to be stable enough to keep the young star together as it grew. Earlier models had failed because they could not find a way to balance the mechanisms that were pulling the gases in and pushing heat out. As a result, these models ended with the young star disintegrating. GMCS are vast regions of the galaxy filled with hydrogen atoms and molecules mixed with specks of dust and ice. Typically, a GMC contains 100,000 solar masses of material, which is a mixture of primordial gases produced by the Big Bang and the remnants of long-dead stars. GMCS are mostly found in the spiral arms of a galaxy. In the mid-1960s, Hsu and the renowned Chinese-American mathematician Chia Chaolin modeled the rotation of a spiral galaxy, and showed that the arms are located at density waves, traffic jams, of stars. Such density waves sweep up interstellar material into GMCS, and this triggers the formation of stars. The impact of a density wave, or something more violent such as a blast from a nearby supernova, creates turbulence inside a GMC. However, highly tangled magnetic fields run through the cloud, and these stop the turbulence from ripping the cloud apart. The magnetism also acts to prevent the cloud from collapsing in on itself under its own gravity. Cloud cores. Over millions of years, the magnetic pressure and turbulence in the gases dissipate, creating regions of calm, where slowly rotating cloud cores form. On closer inspection, GMCS are not uniform, but made up of dark fragments or clumps of denser material, known as Bok globules. Each globule is thought to contain several cloud cores. Hsu's model supposes that the core becomes a single isothermal sphere, or something very close to it. This means that the gravity pulling the ball of gas together is balanced by the outward pressure of the moving gas and its magnetic forces. Such a state can never persist for long, and the contracting gravitational force in the core wins out over the outward pressure. The inner region of the cloud core contracts to form a dense ball of gas at the center. This is the protostar. Protostars do not form in a rapid process, but take millions of years, and millions more to grow into a full-fledged star. The protostar is also surrounded by a disk of material formed by the system's rotation, and wave upon wave of material is pulled in from the surrounding envelope of gas. With each wave, the mass of the protostar and its more diffuse disk grows, and its gravity grows with it. The increasing gravity steadily pulls in material from farther away, hence the description of the process as an inside-out collapse. Frank Hsu's inside-out model describes the four-stage formation of a star from a giant molecular cloud. The star gathers mass. The protostar warms up as it becomes denser, but it is still too small and cold to produce energy by fusing hydrogen in its core. The force of all of the new material landing on its surface also adds to the heat signature given out by the protostar. At this stage, it is giving out only faint infrared and microwave radiation, which makes it hard to see. Eventually, however, the protostar gathers enough mass for fusion to begin, but initially only the deuterium, a heavy isotope of hydrogen, begins to burn. Unlike an adult star, A protostar releases its heat entirely by a process of convection. Heat from its core rises up to